Look up at the night sky on a clear evening. What you see feels anything but dead. Stars burn steadily. Galaxies spin in elegant spirals. Light travels enormous distances just to reach your eyes. Time flows forward, clocks tick, atoms vibrate, and energy moves from one place to another as if the universe itself is busy, active, alive, and endlessly productive. At first glance, the universe does not look like something that is dying. It looks like something that works. For thousands of years, humans interpreted this motion as proof of permanence. Ancient civilizations believed the heavens were eternal. Even today, despite everything we know about cosmology, it is difficult to shake the feeling that the universe is stable, perhaps even infinite in its ability to continue. But modern physics tells a quieter, more unsettling story. The universe is not breaking down dramatically. It is not rushing toward collapse. It is not counting down to an explosion. Instead, it is slowly doing something far more subtle. It is wearing out. A universe full of activity. The modern universe is defined by motion and transformation. Inside every star, nuclear fusion converts mass into energy. Hydrogen atoms are crushed together under immense gravity, releasing light and heat that travel across space for millions or even billions of years. Planets orbit those stars in predictable paths. Galaxies collide, merge, and reshape themselves over cosmic timescales. Even the emptiest regions of space are not truly empty. Particles flicker in and out of existence, and radiation drifts silently through the void. On Earth, this cosmic activity translates into life. Energy from the sun drives weather systems, ocean currents, ecosystems, and biological evolution. Chemical reactions power cells. Electrical signals move through your nervous system. Every thought you have is, at its core, a controlled flow of energy. This constant motion creates an illusion of reliability. If energy is always moving, always changing form, then surely it can keep doing so forever, right? Physics says otherwise. The hidden cost of energy. Every process in the universe, no matter how efficient it appears, comes with a cost. When a car engine runs, some energy becomes motion, but some is lost as heat. When your phone charges, not all electrical energy becomes stored power, some escapes into the surrounding air. When stars shine, enormous amounts of energy radiate outward, never to be gathered again. This loss is not accidental. It is not a flaw in engineering. It is a fundamental rule of reality. The universe allows energy to move and transform, but it does not allow all of that energy to remain useful. This distinction between energy that exists and energy that can do work is one of the most important ideas in all of physics. And it is the key to understanding the eventual end of the universe. At the moment, the universe is rich in gradients. There are hot stars and cold space, dense planets and empty voids, high energy regions and low energy regions. These differences make motion possible. Energy flows from where it is concentrated to where it is spread out, and in doing so, it powers everything we observe. But gradients do not last forever. Every flow reduces the difference that made it possible in the first place. Time's one-way direction. One of the strangest features of reality is that time has a direction. You remember the past, not the future. Broken objects do not spontaneously reassemble. Heat flows from hot objects to cold ones, never the reverse unless additional energy is supplied. These patterns are not habits, they are consequences of physical law. At the heart of this one-way behavior is a concept known as entropy. Entropy is often misunderstood as disorder, but a more accurate description is energy spread. As time passes, energy becomes more evenly distributed. Concentrations flatten out. Extremes fade. Low entropy corresponds to usable structure, systems that can change, react, and evolve. High entropy corresponds to equilibrium, systems that have nowhere left to go. The universe began in a state of remarkably low entropy. That fact alone is one of the deepest mysteries in cosmology. But from that initial condition onward, entropy has been increasing, relentlessly and irreversibly. This increase is not dramatic on human timescales. It does not announce itself with explosions or collapses. Instead, it accumulates quietly, behind the scenes, governing every physical process without exception. Entropy is the reason why motion slows, why systems age, and why nothing lasts forever. Why the universe appears stable. If entropy is always increasing, why does the universe still look so energetic? The answer lies in scale. The universe is vast beyond intuition. Stars burn for billions of years. Galaxies evolve over timescales so long that human history is barely a footnote. On these scales, entropy's progress feels imperceptible. It is like watching a mountain erode. Stand there for a minute, and nothing seems to change. Stand there for a lifetime, and it still looks solid. But over millions of years, the mountain is worn down grain by grain, carried away by wind, water, and gravity. The universe is doing the same thing with energy. Every star that shines reduces the amount of concentrated fuel available in the cosmos. Every reaction that occurs spreads energy a little more thinly. Every moment that passes nudges the universe closer to balance. Right now, the universe is still young enough to be dramatic. Stars still form. Galaxies still glow. New structures still emerge from old ones. The night sky is full of light, motion, and apparent vitality. But this phase is temporary. And importantly, it is temporary not because of chance, but because of inevitability. The illusion of endless time. Human intuition struggles with deep time. We measure existence in years, decades, centuries. Even geological timescales, millions of years, stretch the limits of our imagination. Cosmic time, however, operates on an entirely different level. The future of the universe extends trillions upon trillions of years beyond the present. Against that backdrop, everything we know exists near the beginning of the story. Stars like the Sun are middle-aged at best. Galaxies are still actively forming new stars. Even black holes, the most extreme objects known, are far from their final state. From this early vantage point, the universe feels resilient. But physics does not care about feelings or perspectives. It cares about totals, limits, and final states. And according to our best understanding of thermodynamics, the universe is moving toward a condition where no meaningful change is possible. Not because it runs out of energy, but because it runs out of usable energy. A future without events. Imagine a universe where nothing happens. No stars ignite. No planets orbit. No atoms combine or break apart. No temperature differences exist between regions of space. Everything is perfectly uniform, perfectly balanced, and perfectly still. This is not a dramatic ending. There is no explosion. No collapse. No moment of destruction. There is simply nothing left to do. This scenario is known as the heat death of the universe, and despite its name, it is not about heat in the everyday sense. It is about equilibrium, the point at which energy is so evenly distributed that no process can extract work from it. At that point, time loses its meaning, not because clocks stop ticking, but because ticking no longer signifies change. But we are not there yet. Far from it. At this stage in cosmic history, the universe still has enough imbalance to create light, structure, and motion. It still looks alive. It still feels dynamic. Which makes the concept of heat death easy to dismiss as abstract or irrelevant. That dismissal is a mistake. Why this matters now? The heat death of the universe is not a prediction based on speculation. It is a consequence of physical laws that have been tested countless times, from laboratory experiments to astronomical observations. Every star we observe aging supports it. Every energy transfer we measure confirms it. Every system that moves toward equilibrium reinforces it. Understanding heat death is not about predicting a date on a cosmic calendar. It is about recognizing the direction of reality itself. The universe is not cycling endlessly. It is not preserving its energy in a form that remains forever useful. It is not maintaining its youth. It is aging. Slowly, quietly, and with absolute certainty. In the next part, we will examine the rule that makes this unavoidable, the one law the universe never breaks, no matter how much energy it contains or how vast it becomes. Because once that rule is understood, the end of the universe stops being a mystery and starts looking like a conclusion that was written from the very beginning.